Imagine you wake up 10,000 years ago. No keyboard, no screen, no idea where you are. You look down, in your hand is a nicely shaped rock, and your mission is to build a computer, not a calculator, a real working programmable computer. You look at the rock looks
Mhm.
back at you. This is going to take a while. Step 1, don't die. You already know the drill. Survival first. You chip the rock into tools. You build shelter. You figure out which berries won't kill you and which animals will. You get hurt more times than you'd like to admit. But here's the thing. You can't invent anything while you're running from wolves. So you do what every civilization has done before you. You become a farmer. You clear land, plant crops, domesticate animals, and for the first time in your life, you have a surplus. Extra food, extra time, extra brain power that isn't being spent on not dying. You're still roughly 9,800 years from a working computer, but now at least you can think. Step 2, metal. One afternoon, you notice strange, heavy, colorful rocks scattered on the ground. They look almost decorative, completely useless, until you throw one into a fire and something inside it melts. That changes everything. You build furnaces. You burn wood into charcoal to push temperatures higher. You experiment with copper, with tin, with iron. Failing constantly, succeeding slowly, you learn to smelt, to pour, to forge. Metal tools replace stone ones. Eventually, you're not just surviving, you're building. Step 3, math. Here's the uncomfortable truth about computers. They are, at their core, math. Billions of tiny math problems solved so fast it feels like magic, and you have none of that yet. So you start from scratch. Counting comes first, then arithmetic, adding, subtracting, multiplying, then geometry. You work out angles and areas, realize that shapes follow rules, and that those rules are consistent whether you're building a barn or measuring a field. You write things down so knowledge doesn't die with you. This is quietly one of the most important things you will ever do. Then you go further. You study how things move and change, how a thrown object arcs through the air, how rates of change have their own rules. Without meaning to, you've reinvented calculus. You weren't trying to, you were just curious. Curiosity is the engine of everything that comes next. Step 4, electricity. You've seen lightning your whole life. You've felt the shock from touching a doorknob on a dry day. You've watched a compass needle swing toward a lump of iron. These aren't separate mysteries. They're the same mystery. You rub materials together and study the sparks. You build coils of wire and move magnets through them. Something moves, a current, invisible, powerful, and suddenly yours to control. You figure out voltage. You figure out resistance. You figure out that some materials carry electricity freely and some refuse it entirely. You're not just playing with sparks anymore. You're learning the grammar of energy. You build a battery, crude at first, layers of metal and salt water, but enough to keep a current flowing without stopping. For the first time, electricity is something you can have on demand, and now you can start doing something with it. Step 5, switches. Here's the idea at the heart of every computer ever made. A switch. On, off, yes, no, 1, 0. A switch that's on means something. A switch that's off means something else. String enough switches together in the right pattern and you can represent any number, any letter, any instruction. That's it. That's the whole idea. The first switch you build is mechanical, a physical lever that connects or breaks a circuit. Then you build smaller ones, then faster ones. Then you realize that electricity itself can act as a switch, that a current flowing through one wire can open or close a path in another. This is the relay. Thousands of them wired together can do simple logic. Add this number to that one. Compare these two values. Decide which path to take. It's slow and loud and fills an entire room, but it works. And it works because the logic is real. There's a branch of mathematics, Boolean algebra, that treats true and false as numbers and or, and not as operations. You work it out on paper. It looks like philosophy. It turns out to be the instruction manual for every computer ever built. Step 6, transistors. The relay is too slow, too big, too fragile. You need something smaller. You've been sitting on the answer the whole time, but it required a detour through chemistry to find it. Silicon. It's basically sand, the second most abundant element in the Earth's crust. And on its own, it's almost useless. It barely conducts electricity. But when you add tiny, precise amounts of other elements, a process called doping, it changes. You can control whether it conducts or not. You can make it switch. Here's the catch. To make silicon useful for computing, you don't need it mostly pure. You don't even need it very pure. You need it almost perfectly pure. Something like 99.99%, with impurities added back in exact controlled quantities. That level of purity requires industrial processes you haven't invented yet. Furnaces that run at 1,400 degrees, clean rooms with no dust, crystal growth machines that pull a perfect cylinder of silicon from a molten pool at a rate of a few millimeters per hour. So you invent those two. You grow your first silicon crystal, you slice it into wafers, you etch tiny patterns onto it using light and chemistry, a process called photolithography. You build the first transistor, 3 tiny regions of silicon that let a small current control a much larger one. One transistor is interesting. 1,000 transistors is powerful. 1,000,000,000 transistors on a chip the size of a fingernail, that's as a processor. Step 7, the chip. This is the part nobody talks about. You etch billions of microscopic transistors onto silicon using light, precision optics, and some of the most advanced manufacturing ever created. To do it, you build an ultra-clean fabrication plant where even a speck of dust can ruin a chip. You design the architecture, the logic, and the pathways that let data move and calculations happen at incredible speed. You power it on for the first time. It works. Step 8, memory and storage. A processor without memory is like a person who can do math but can't write anything down. You build RAM using transistors that store a 1 or a 0, switching billions of times per second. It's incredibly fast but temporary. Turn off the power and everything disappears, so you create long-term storage. First magnetic disks, then flash memory, where trapped electrons can hold data even without power. Now your computer can remember things. Now it can save. Step 9, software. After all the mining, chemistry, physics, and fabrication, the thing that makes a computer useful isn't hardware, it's language. At first you program in binary, raw ones and zeros. It's painfully difficult, so you invent assembly language, then compilers, then an operating system that manages hardware, runs programs, and makes everything work together. You write the OS from scratch, then you write a program. The screen lights up, text appears, the cursor blinks, it's done. After thousands of years of farming, metallurgy, mathematics, physics, chemistry, engineering, and software development, now you have a computer. Most people think the computer is the invention. Really, it's the result, the endpoint of an unbroken chain of human curiosity, from the first stone tool to the engineer who etched billions of switches onto a piece of sand. Every click, every scroll, every program that opens instantly, that's thousands of years of work, and it all started with a rock. Now, if you'll excuse me, you have a computer, and you've earned the right to waste it watching videos about making computers from rocks.